So, Phil, thank you for being with us. The first thing I would want to know, and maybe what the students want to know, is when did you decide that you were going to go into a career like this, and what are some of the different steps that you took to get there?
Well, my entry into biomechanics and exercise science was kind of serendipitous. I was a gymnast on the Australian team, competed in Montreal in the Olympics in '76, and after that, I decided that I wanted to go for the second Olympics in 1980. So I came over to the United States in '79 to actually compete and qualify. And one of my teammates was on the Arizona State University gymnastics team. So I went to train with him. And they had a biomechanics group there, and they showed me some images of stick figures of motion for different sports, like throwing and jumping and running. And I looked at that and I thought, that's pretty cool. I could do that for my gymnastics. And at the same time, the coach, Don Robinson of the gymnastics team, was interested in having me stay as an assistant coach. So it turned out that I was able to stay and be the assistant coach on the team and continue training for the Olympics in 1980 at the same time as I was doing my master's degree in biomechanics. Just
Very
lucky,
interesting.
right place at the right time.
But Phil, what is your undergraduate degree in?
Well, my undergraduate degree is in electrical engineering, so that was kind of convenient too. I didn't end up going into the electrical side of it, but having the engineering background, the math, the physics, the computer programming, all of that sort of thing really combined and made biomechanics just the perfect choice. Because while I was doing my master's degree, I helped develop the software to pull together all the equipment and create a motion analysis system that I was able to use to do my thesis, my master's thesis, which was the biomechanical analysis of the handspring front somersault vault. So I got to do gymnastics for my master's thesis.
Yeah, so you got to take what you love and what you do,
Exactly.
tie it to your two disciplines now, engineering and biomechanics, and voila.
Yeah, exactly.
Very interesting. So can you talk with us a little bit more about your software? So I know this was a big pivot point for the technology at the time in the field. So can you talk with us a little bit more about the instruments or how that's used and what applications that software has?
Yeah, it did turn out, I didn't know it at the time, but it did turn out that I became one of the pioneers in the motion analysis industry because it was really in its fledgling phases at that point in time. We had a computer and a digitizing tablet and a projector and a high-speed camera, and none of them were connected. So I had to connect them together and write the software to make them work. So what we would do is we'd go and film the handspring front somersault with a high-speed camera at 300 frames per second, and then we'd project the images from the camera one frame at a time onto basically a screen, and we'd put the crosshair cursor of the mouse on each of the joints. So as the athlete is running and jumping, you'd tag the shoulder, the hip, the knee, the ankle, the toe, the wrist, the elbow, and you get a stick figure. Click the button, get the next one. Click the button, get the next one. Now, it wasn't very exciting. It was very boring. It would take me about an hour to do one skill. But the cool thing is, by the time I was finished, I was able to track the center of gravity of the gymnast going over the vaulting horse. I was able to calculate the angular velocity, the angular momentum. One of the cool things that we discovered that we didn't really know at the time was that the center of mass, or the center of gravity of the athlete, the gymnast, did not come down onto the horse. A lot of people thought it went up, came down, and then you pushed back up again, and then you did your front somersault. Truth of the matter is, you kind of tap the horse on the way through, and you just keep going up. And so by looking at the trajectory of the center of gravity, I was able to prove that as one of the things in my master's thesis.
Very neat. Just fascinating. And this is kind of jumping ahead of myself a little bit, but one of the questions for later was, where is the technology or the things that you work with, how is it evolving and where is it going? But in this instance, you were one of the people that pioneered this technology. Where is it now? Where is it going?
Well, I can give you a quick step-by-step, and it's just amazing where it's going now, because I said we did it with film. The next step when I worked for the U.S. Olympic Committee in Colorado Springs was we did it for video, so we didn't have to use film anymore. Now we could do video. The cool thing with video is the images are captured and put into the computer, and once they're in the computer, they're basically just a series of ones and zeros. So anything that's white on the screen was like 256. Anything that's black on the screen was 0. So to find all the white markers, we put those white ping pong balls on the joints, and we'd shine a floodlight so they'd fluoresce. and then you'd see the bright spots on the screen. You didn't have to now go and track those manually. The computer could search through the screen like searching through a big spreadsheet, looking for anything that was over 200. Any number that was over 200 was pretty close to white, and so that was a marker. And so we'd then find all of those pixels, and then just find the centroid and move on. And the computer could do it way faster than we could. So that was the next evolution. Then the next evolution after that was to take 2 cameras, or 3 cameras, or 4 cameras, and film a calibration, a 3-dimensional calibration frame, and then allow the computer to digitize each of the cameras automatically, put that data together, and now instead of just X and Y as in 2 dimensions, now you have X, Y, and Z. So now you can get 3 dimensions, which whenever you're doing, if you're just running along in a straight line, 2 dimensions is okay. But if you're a diver or a trampolinist or a pole vaulter or I don't know, a javelin thrower or a shot putter, you're spinning around in circles. You're not staying in one plane. So we have to analyze you in 3D. So that was the next advance. And that happened, the late 80s, early 90s. And then the next step past that was let's not use video anymore. Let's come up with sensors now. Let's do either electromagnetic sensors or inertial sensors such as accelerometers, gyroscopes, magnetometers, all that sort of thing in the early 90s started coming to fruition. The problem with the video system and the cameras was the little markers, they get lost. If you've got one on the back of your hand and you turn your hand over, the camera can't see that anymore, so it can't track it. Whereas with inertial sensor and electromagnetic sensors, the body is pretty much transparent, and so it can track them automatically all the time.
Wow.
And plus, you can't really take those cameras outside. Well, you can, but it's difficult to set up 10 cameras outside. Whereas if you put inertial sensors and strap them on, you can run around, walk around.
So you're able to do more field testing now
More
instead of being stuck in the lab.
Exactly, yeah.
That is so neat. I jumped ahead, but that was a great piece of information. So, Phil, just on a day-to-day, we know you work with the Olympic athletes. So give me an idea of what your day looks like. You get to work at the training center. What are you doing? Who are you working with? And what are some of the outcomes that you're measuring? And what are some of the goals of those outcomes and what you're measuring?
Okay, well, I've been working at the Olympic Training Center for about 6 years now, and my primary role is as a sport technologist and biomechanist. So there's kind of 2 roles there. The technologist portion of my day is basically hunting around on the internet for all types of new technology, whatever I can find, whether it be physiology technology, sports psychology technology, or biomechanics technology. Of course, I'm favorable to biomechanics because that's my area. So I'm always looking for the new and the latest and greatest technology, and then getting in touch with those companies, getting in touch with those universities, going out to see them, seeing what the technology is, and convincing them to help us develop new technology directly for the athletes. Now, on my hands-on portion of my day-to-day, where I actually work directly with the athlete, and I'm very lucky that I've got both of these roles, 2 or 3 times a week I'll go down to training, and I'll work directly with the athletes. If I'm working with sprinters or the long jumpers, I use a device called the OptoJump. And effectively, it's a series of light-emitting diodes, LEDs, and photocells, and you lay the strips down, and they run between the 2 strips. And effectively, it's like a garage door. When you break the beam, you open the garage door. In this case, when you break the beams, it tells you where your foot is. So it knows when your foot went down, when it went up, where it was. So it knows your stride length, your stride rate, time on the ground, time in the air, and whether you've got any asymmetries or not. And from that, we can calculate velocities and accelerations. So we use it a lot for long jump, the run up in long jump, the run up in pole vault. They don't want to stutter step at that last step. They want to have a good, even step. They want to accelerate into the last step, and we can help them immediately. And of course, it takes the video at the same time as well. So they can come back, look over my shoulder, and then have a look at their technique. And then I can say, well, you slowed down. Look at the bar. It gives a bar chart of their velocities. And you can say, well, look, you slowed down a little bit, and your step length was a little bit shorter there. So stride out, move your run back a little bit, whatever. Turns out I worked with Jeff Henderson, is one of the guys I worked with. And he became a gold medalist in Rio by 1 centimeter. He won by 1 centimeter. That's one fun story. The
that
other
is exciting.
I am such a lucky person to work with these types of people, these types of athletes, and these types of coaches. It's wonderful. You kind of look back at your life and you say, hey, I'm doing exactly what I was trained for. Very
That's
lucky.
right. And that's why you're here talking to students, because a lot of them want to follow in your footsteps. They just don't know how to go about doing it. And so you're here to show us that the dream does come true as long as you stay diligent.
It can. You can stay with it. And the technology just keeps on coming. There's one other thing, just one quick other story. We developed a device called the TrackMan. Actually, we had it modified for track and field. It's been used in golf. Whenever you watch the golf on TV and you see that ribbon that tracks or traces where the ball went, they're tracking the ball with radar, and that's a device called TrackMan. We wanted that for shot put and hammer, and so we paid them a bunch of money to develop it for hammer and shot put. And over the last 2 years, we've been using it at the training center, and it gives you information immediately. It takes your video and calculates the distance that the shot put went, the angle, the velocity, the direction, and the height of release. And if you know anything about your physics and your trajectory motion, which I think you all learn about in projectiles, that sort of thing, you can calculate the flight of the shot put from just those 5 individual inputs. So we could tell them exactly what the optimum release angle was, what the release velocity was, and we worked with, again, luckily we had 2 of the best shot putters in the world at the time. We worked with them over a period of couple of years. And in Rio, we had success again. We went gold and silver with those 2 guys. And gold actually took the Olympic record, which was about 30 years old. So pretty exciting time. Very exciting time.
Super exciting time. So we know you love it. And so I probably don't have to ask you your favorite aspect of your job, but is there any big drawbacks, or what is the limitations that you have, it could be personally, financially, whatever it is, what's been a hardship in the road you've traveled with your career? Any at all?
Well, after I worked for the Olympic Committee, I went into my own business, and running your own business is always difficult. And so, unfortunately, I was not actually successful. I didn't become a millionaire or anything like that. We survived for 20 years developing motion analysis systems. But I guess the downside is, when I was going through that period, it's pretty much a niche market. Human motion was not very popular. I mean, when you say to somebody, I'm a biomechanist, they say, oh, do you fix cars, or something like that. They don't really know what it is. However, that being said, this is the 21st century now. And I think human motion is getting easier and easier to measure with magic cameras now. We can point a camera like the Microsoft Kinect, that video game where you can dance in front of it and it tracks your body and scores your points on how good you dance. We can, not we, but there are people writing software so that you can do physical screens with that. Can you touch your toe? Can you rotate your shoulders? And effectively come up with a program for physical therapy to improve on any of the physical issues you might have. So what I'm saying is there's more and more and more avenues for biomechanists and exercise scientists to go into, whether you go into industry now, whether you go into academia now, or whether you're lucky enough to get involved with one of the high-level professional sports or Olympic sports. So there's more and more. I would say it's a good time to be doing exercise science. I mean, you can end up in physical therapy, you can go performance, you can strength and conditioning. There's just so many areas now.
There are, Phil. And one last question for you. If you could give one piece of advice to a very young undergraduate level student, a way to get involved with biomechanics, what would that advice be? Would it be to take extra courses in an area, to get involved with research, to get out into a professional practice group or membership? What would be your best advice for how to get these guys on the right path to do what you do?
Well, I have one of your students, Larry Kennard, that actually came out to the Olympic Training Center, and he just said, hey, I want to volunteer. I'll come do whatever you want me to do. And so he worked with me a few hours a week to start with, and I just got to know him. And then he took an internship, and then a part-time position came available. So I guess the moral to the story, it's hard just to send your resume out. People look at a resume, they have no idea how good you are. You've got to get in front of their face. You've got to do internships. You've got to volunteer.
Phil, thank you so much. I feel like we've covered a good amount of what you do, who you service, what the data that you collect is used for, and some of the technology that you use to collect it. So thank you very much for talking with us. We appreciate your input and your wisdom.
You're welcome.